In this lecture, we'll be taking a closer look at the applications of geomorphology as they relate to streams and stream actions. The topic of the geometry of a stream or a stream channel is rather extensive. There are a lot of factors to consider, and it's important that you couple the content of this lecture with your weekly readings. Probably the most important aspect of understanding hydraulic geometry is to pick apart, to understand more closely, the nature of stream channels, their depth, their width, the stream's velocity at any given point, and of course the suspended load, or the load that the stream section or the order of stream that you are studying is carrying at any given time. It's also important to keep in mind that these variables will fluctuate by season and the nature of local climates and weather patterns. A very important variable to consider when you're looking at stream action is watercourse surface area. This is a variable that is important to the creation of stream hydrographic models. Basically, it is an estimate of the area of exposed flow within a drainage basin. Hydrologists will accomplish the gathering of this data by sampling a stream with a series of random samples or random areas within a drainage network. They're looking again at the volume of flow that is moving through any one point, and they're considering that in relation to the overall width of the channel itself. Again, the channel that contains water, exposed water. As is the case with other variables that we're collecting, when we're taking a look at the nature of a system of flow, things like scale, for example, we have to specifically gather surface area as it relates to a stream order. So we have to really look at the entire drainage system and segregate it down into its varying stream orders. Then we focus on segments within that system of flow and estimate, in this case, surface area for each order. When that is accomplished, we then gather all of that information together and estimate a total surface flow for the drainage network. Sinuosity is another important measurement. This again is a ratio of the overall length of a stream to, in this case, the overall length of the flow itself. So when you take a look at how sinuosity is determined, generally you are estimating two things. First of all, how much ground is ultimately covered within the drainage system by a order within that system of flow. So in this case, when you take a look at the diagram, you can see a point A and a point B. One of the first recordings that we have to take is the overall length of that flowage. And then we run a line parallel to the actual flow itself. This will include the any meandering that occurs. There will be fluctuations in the overall angle of the meandering flow, and we get a sense of that overall length. The ratio then of the meandering length to the kind of point A to point B straight line distance that the flowage is covering within a drainage system gives us something to measure, an index that will be tied to this term or concept. So what this is doing is ultimately it is giving us a measure, and it's in the form of an index or a ratio for the irregularity of a stream or stream action. When a stream flows in a linear fashion, it is ideal, yet we know this is very uncommon. A channelized system of flow would have almost a measure of 1. If the river parallel distance was to increase significantly, what will happen to the index? Well, the numerator in this case will increase in value. So we'll see a much higher number, and that higher number, in a sense, will help us to, again, gauge how much meandering is occurring in that area within the drainage basin. So another way of thinking about sinuosity is to consider this. Basically, the numerator would be the flow length, and the denominator would be the actual length of the valley itself, the valley where the stream is found. Generally, how do we measure these? We measure the flow length by traveling along the channel. We begin with the lowest order, tributary, and then working our way toward eventually an area of discharge. The valley length then is something that can be estimated off of an aerial photograph or off of a map, similar to the ones that we're looking at in lab and in class as well. And generally that is going to be, again, the distance from maybe a high elevation where we see a headwater area to a lower elevation where we're seeing either that segment of flow working its way into another order within the larger basin itself, or if we're taking sinuosity into consideration for the entire basin, then we would take a look at that area of discharge, final output, the mouth of the river, for example, if that's what we were looking at. The Honey Creek becomes a very important topic just because so much of what we look at in a variety of courses at Wisconsin Lutheran College is assessing its health and the impact of eutrophication on at least the Wauwatosa segment of that segment of flow. When we take a look at the Honey Creek, again, we generally are looking at a first order flow. We can look at this in terms of a USGS map setting, or we can literally walk out or drive out to a section of the flow. And again, we identify it as being an initial tributary in terms of what eventually becomes the Menominee River itself. The Honey Creek is interesting because, as many of you know, the system itself has been modified. It has been channelized in a variety of ways. Some of them are architectural, others are a combination of natural and man-made processes. So we have to take these into consideration, and ultimately these considerations will help us to better understand the health of the flow and how plants and animals interacting with that section of the larger drainage basin are able to, in a sense, either thrive, or if there is something that needs to be corrected, to be able to bring that area as close to a more natural environment as possible. So sinuosity, in a sense, allows us to make some general judgments with regard to the kind of a flow that we will see in any segment of a larger basin. It will also give us a sense of the overall load that can be carried in a segment of flow. As I said before, sinuosity measures that are at or near 1 or a 1-to-1 kind of ratio. These are recognized to be ideal, and generally these are things that are very rare to find in nature, or they are rare to be naturally occurring in a sense. However, they are considered to be the most efficient systems of flow when we look at how water is interacting with the landscape, how water is interacting with local changes in elevation, and then of course how water itself is transporting materials that have been eroded from areas of very high energy, maybe higher elevation, to areas of lower energy or lower elevation. When a sinuosity ratio approaches 3 in terms of this index value or greater, generally geomorphologists will recognize the area of flow to be tortuous in nature. These are flows that are in a state of dynamic equilibrium, and they are sites of significant erosion and deposition, full of twists and turns with varying measures of turbidity and flow velocities. When you take a look at this particular resource, this figure here, it gives you a good idea of the interplay between flow, between the overall physical nature of a channel, and load. When we have a fairly channelized expression, as we do in example number 1, we note that generally this will be an area of low stability, with regard to the load that's being carried. The load generally will be in suspension. And we will most likely find either the greatest measure of load or the largest particles that are held aloft in the flow as you move from one segment to the next. As you start to move, bring your eye, for example, from number 1 across this diagram to number 5, you start to see higher stability being expressed, but you also start to see a lot of meandering and very volatile kinds of deposition with regard to the material that is being, again, carried aloft in the flow itself. And again, as I've mentioned before, this can be physical particles, but it can also be chemical load in a system of flow as well. If you look back on the left-hand side of the diagram at a generalization regarding the channel pattern itself, and you move from the bottom of the illustration to the top, you will note that there will be an assumed change or fluctuation in things like elevation, and ultimately there will be an assumed fluctuation in terms of the ratio between the width and the depth of a system of flow. This means that in our hypothetical example, if you're dealing with an area of high elevation or an area that has a fairly high expression of gradient or slope, you will see a lot more channelization occurring, or as close as you can get to channelization in a natural system. You'll see a lot more suspended flow in terms of measures of turbidity, what ultimately is being carried aloft in that segment of the flow or the segment that you're studying. You will also see a very high ratio then between measurements of channel width to channel depth. So you'll see, for example, much deeper channels in these areas where we have a much higher change or much greater difference in elevation from point A to point B in an area that we are studying with regard to stream action. When we begin to move from an area that has a pretty significant measure of gradient, we then start to see a little more of this meandering occurring until we get to almost a braided system in these flows, and we see gradients then being at their lower or lowest measures within a basin, and generally we will start to see a lot of load being dropped as we move energy-wise into a part of the flow system that has expressions of very low energy. Your course text will include similar diagrams, and I challenge you to take a look at those, pause in your studies to be able to really begin to look at how these variables interact with one another. Because again, when we are out in the field gathering data for these hydrographic models, we take into consideration all of these qualities with regard to a local landscape. What is the overall change in elevation between a point that we start our observations and a point closer to where we are concluding our study? What are the overall expressions of channel width or even bed width regarding a system of flow? And then we will consider that variable in relation to the overall depth of a flow, and we'll be talking about Thelvig in just a moment as well. So these are all qualities that we have to consider almost at the same time when we are assessing why a section of an open water, terrestrial water expression is moving in the way that it is, or has the physical qualities that it does. And then when we look at the content of the flow itself, how much material is actually being carried, or the relationship between the load of that flow and what we might be seeing at higher elevations or elsewhere within a drainage basin where we have erosion. And again, this becomes very, very important for people who are planning an area and looking at qualities such as impact as they relate to um, eutrophication, erosion, um, development with regard to building plans for a floodplain environment, for example. All of these things become extremely important characteristics as we assess or even predict, attempt to predict how a system of flow will evolve over time. What you will find is that the majority of flow environments, at least those that are fairly unmodified, will be in some systematic state of dynamic equilibrium. Take a closer look at this diagram here. This will allow us to further blend some of these ideas and include the concept of Thelvig as we begin to consider the depth of a system. It is important to note that stream depth, another very important variable that we will record as we study a flow environment, stream depth is very much tied to measures of sinuosity. The lower the sinuosity measure, the deeper the flow. Again, we're getting closer to a more channelized environment. And of course, there's quite a bit in between these rather extreme examples. When we're talking about channel depth, generally we have to use or utilize this term Thelvig. As you can see here, Thelvig is an expression or a concept that relates to the line that connects points of maximum water depth in a variety of downstream points within a channel and throughout a channel. Generally, when describing channel habits and trying to predict how a channel will behave over time, as it begins, let's say, to meander quite a bit more, as it becomes um, more stable ultimately in terms of load and flow, Thelvig becomes a very important consideration. Most Thelvigs pass through a succession of pools in a channel body, and they are separated by riffles, which might be associated with, in this case, the development of sediments and eventually sedimentary rock. So even how we understand the nature of sedimentary rock and how it forms, this idea of high and low energy environments within a system of flow as it relates to channel width and ultimately channel depth, all of these become very, very important. Now what you'll see here in this diagram as well is that Thelvig is going to be measured theoretically within um, the flow itself. It's a maximum depth, so it's not always in the center of the flow. If you have a very meandering kind of environment where you see a lot of alluvial deposits, the development of point bars, um, you will find that Thelvig is going to be generally assessed furthest away from those areas of deposition. Just because it's going to be an area where you have a deeper segment of the flow and you will have things like velocity increasing. The water itself, the water system itself, will be able to ultimately carry more load suspended. And so it will be further away from more shallower areas where we start to see alluvial deposits and even the emergence of these submerged bars, which eventually become point bars or segments of developing land environments, alluvial land environments within a local landscape. And it is because of this very unique relationship between the depth of flow and the velocity, the velocity of flow with regard to a segment we're studying. It's this relationship that helps us to understand when and where even more extreme expressions such as braided streams will develop. So a stream system that is in a braided kind of morphological structure is kind of the opposite to areas where we see a very significant measure of depth. Braiding again demonstrates that flows are shallow and that stream load is fluctuating, in this case becoming significantly diminished. Here is a Landsat image of a section of the Congo River Basin. In this case, this would be associated with the northwestern border of what is today modern Zaire. It demonstrates how braiding can occur and how it can really have, on a very large scale, a pretty significant impact on the development of a fluvial landscape. And again, when we take into consideration all the variables that we are looking at when we are applying stream geometry or stream geomorphology, again, we find relative expressions of relative stability in this case to be quite low in terms of overall stream depth and ultimately what's happening to the load within that segment of a flowage. The last characteristic that we will take a look at with regard to the geometry of a hydrological system relates to stream process and form. Ultimately, how the stream flows when we are taking a look and trying to understand something about how a drainage basin is evolving, we have to start to consider the kinds of channels that are common throughout the varying orders of a drainage system, and then ultimately the kind of load that is being either suspended or deposited throughout this system. In this case, stream power, or ultimately the potential power that is being expressed within a fluvial system, becomes extremely important. And it is something that on a geomorphological level we have to start to assess. And this takes into consideration a number of variables that we collect in the field. Some of these are less practical than others, but ultimately they give us a really good understanding of the potential energy that is bound up within a drainage basin. So one of the first things we have to do is take a look at the overall basin itself. What's that geographical space that's being drained, in this case, by a system of flow? And of course, this begins to take into consideration that groundwater material as well as we're projecting the potential energy outputs. We have to understand something about or estimate the mass of the water and the velocity of the water particles themselves as they relate to changes in elevation and ultimately gravity itself. What are we measuring? Ultimately, we are measuring kinetic energy as it relates to a segment of flow. And again, this value becomes a little less practical in nature. However, it is very important in understanding the different kinds of channels that we come across and that we study on a local level. The channels themselves will ultimately be organized, and the larger landscapes that they are a part of will be organized by the kind of transport, the kind of load, and the kind of deposit that we see on a regular annual basis. So to the kinds of deposits that we recognize within a larger drainage basin become part of this classification scheme. We start to see where or the nature of deposits as they relate to channel margins. We start to assess the kinds of deposits even after the fact, after a natural event has occurred. The kinds of deposits that would be associated with a flooding event where a channel is overcoming the channel banks itself. And we start to assess ultimately what's happening to a river valley or the basin itself. We can take a look at deposits that are, in a sense, associated with major slope wash and soil creep in an entire landscape that is considered to be fluvial in nature, so a floodplain or a valley system that's associated with a river that is ultimately um, meandering through that landscape, but then also modifying that landscape over time. So when we're looking at the overall volume of suspended material, in this case physical material, it is important for us because it helps us to understand, where a landscape is in its overall evolution in terms of a fluvial landscape. And then it gives us an understanding, some of which is a little bit hypothetical in nature, but a deeper understanding of the interaction between energy and matter within a drainage system. So in this case, we have three channel environments that are organized or classified in terms of the amount of suspended load that is in transport. In the case of, for example, a straight or channelized environment, we see quite a high expression of suspended load. This is generally because we have, again, a lot of material that's being carried along by a rather, um, in this case, fast flowing system of the drainage. Generally, we'll see little to no deposit. So deposit in this case, in terms of the overall sediment material within the stream bed itself, will be less than 3%. If we do see any deposit, it will probably be the largest of the material, at least the physical material that's being carried along in the flow. On the opposite side of the more extreme suspended load environment, we have a bed load environment. This is where we have a lot of the material that is associated with the overall stream bed itself being developed. And we're seeing really all of the major classes of particles being deposited at that time. So a bed load environment would be an environment where we have maybe a braided system that is either developing or fully developed, where we have relatively low measures of stream stability with regard to stream depth and width, or in terms of what we're talking about here, stream process and flowed, in this case, load. In between the two, then we have more of a mixed environment in terms of, again, channel type, or how we classify channels by their flow and load. A mixed environment will be somewhere between 3 and 11% of the total stream bed material, the sediment, being present. What does this ultimately tell us? It tells us, again, something about the nature of energy in this environment. Areas of high energy, high erosion, deep channels, we will see a lot of suspended load channel types being expressed in a drainage basin. As we move further down in that drainage basin to higher orders, again starting it with our order 1 and working our way toward order 4 or order 5, we start to see more mixed loads. And then as we get into maybe a delta environment, which is a pretty good geographical example of this kind of channel, we start to see these bed load channels developing, and these would be similar to what we saw in northern Zaire in that Landsat image. So take a look again at this particular image that I have as this kind of last slide for you to consider. You've seen this before, but again, it demonstrates the interplay between all of these varying variables. We have situations where we have different kinds of and levels of channelization occurring. We have different depths, different widths, and of course we have a changing landscape with regard to elevation and the relationship between that, the water in that, or at least surface water in that landscape, and things like gravity. So they're all interplaying with one another, and they become fairly predictive in nature. When we see let's say a stream order 1 at a high elevation, we're seeing a lot more suspended load. We see a lot more erosion occurring. We see a lot more of this material being carried downstream in more channelized systems of flow. As we move into the center of a flow system, order 2 and order 3, we start to see a little more of this mixed load environment. We start the development, or see the development rather, of different kinds of deposit types at the margins and even within the system of flow itself. And then when we get into these lower elevations where we have little to no gradient whatsoever, and again, when we get to glaciation and we look at outwash plain environments, we'll see a lot of this occurring. We still see it even occurring today as glaciers continue to recede. But we start to see these braided systems where, again, there's very little gradient, and the greatest amount of the overall sediment within a flow system, within a drainage system, is being deposited along the stream bed itself. And we start to see almost island-like bars developing within these very braided flow environments.